Say you'll continue. Okay, so we're going to finish up, we're going to start chapter 8 today. We'll finish up chapter 8 on Friday, and then we'll do our standard any questions before the quiz and the quiz on chapter 7 on Friday, and I'll stay here on Zoom chat while you take the quiz. I must confess that things are a little bit crazy right now. Maybe they're always crazy, but this week in particular is registration. And so I'm getting emails and phone calls and just, all sorts of things to kind of help people get registered for their classes. So I am behind on our rating for the class. So I haven't gone through and graded last week's quiz. You have kind of a baseline score that you can see for the number of questions that were fully correct right at that moment. But I will go through and award partial credit and have those final scores in for you as soon as I can. Maybe later today. I have an awful meeting today. But maybe between class and the awful meeting, I can work on those quizzes. Before 4:30 comes, I really, I'm not super excited about the way that registration works, because priority registration is at 7:30 in the morning, and then regular registration for each, category is at 4:30 in the afternoon. And so like priority registration, maybe student athletes, students in the honors program, like there's some things that put people into the priority category, and that's fine. It's good. That's well and good and fine. But typically during the day between 7:30 and 4:30 is when offices are open and people are around that could possibly help you if you have an issue. And then the vast majority of students don't get to register till 4:30 in the afternoon. And then I get, a flood of emails around dinner time, hey, I can't get into this. Can you open up a spot in this section? Whatever. So I'm not excited about the way we're doing it right now, but do reach out for help if you're trying to get into a chemistry or a physics class. Those are things that I can help you with because I am the chair of the Department of Chemistry and Physics. If it's a biology class, you email Dr. Mercer, chair of biology. Math, Dr. Travers, chair of math. Typically, we try to manage enrollment, and one of the hard things right now, you guys are current existing students registering for seats for the fall, but in the foundation courses, general chemistry 1, physics 1, those kind of things, we don't know who's coming. There's a bunch of newly admitted students who will materialize sometime over the summer. So we try to save seats for as many students as they're predicting will come in. And then so sometimes I'll cap a class lower than it really needs to be capped, just to be saving them some seats. And so if you say, oh man, general chemistry section 3, I really want that one because that other Dr. McTaylor's teaching that one and she must be awesome because you're awesome. If you said that to me, I'd let you in. So that kind of thing. I'm just trying to manage things as best as we can. But obviously you guys, the current students, are a high priority. It just, when new students come in, if they can't get a seat in classes they need, they really freak out. Like, why did you accept me at your school if you're not going to give me a seat in the class I need? And that's a reasonable argument too. So we try to do the best we can with the resources we have, and that's what goes on. So if you're having trouble getting into something you need to get into, reach out to the chair of the department of that class, not the specific faculty member teaching it, but the department chair who has the ability to give you a permission or put you on a wait list or whatever they do in that department. Okay, so here we are. On Friday, we will have a quiz on Chapter 7 material. So I'll field any questions you have on Chapter 7 homework before then. I stuck the Chapter 7 stuff down here lower on our page just so you can look at it if, you know, as you're doing stuff this week. Chapter 8 is what we're doing this week. So we have the homework, the chapter from the textbook that I chopped up electronically, the homework videos, and then the slideshow that I'll be lecturing from, and then just some videos where I blah, blah, blah in a disembodied voice talk through the material from Chapter 8. I don't think there's anything else profound on the page to mention to you. So now I have to find the PowerPoint. I need to put it up top so I'm looking at you when I'm talking. View, reading view, new share. Okay. As always, let me know if you have any questions, and I am recording this lecture and I will post it. So if I say something that's a little too fast or whatever, you can go back and watch it again. I think I've mentioned this before. Let me mention it again. If you choose to watch one of the lectures over again, I would, you know, if you're here for the lecture now and you're engaging in the class as we're going through it, but then you want to review, I would recommend setting it to 1.5 or 2 times the speed. You get through it a lot faster. I at least understand what I'm saying when I put it at that pace. I make myself a little less annoyed listening to myself talk because it's faster, at least, without my pauses that I do. So I'd recommend speeding it up the second time through. So we are into a new, some new concepts in physics. No, how do I say this in a way that makes sense? There were some things that we covered in physics so far that introduced a fundamentally new idea, new units, new, you know, concepts. And my wife is texting me, but I'm going to ignore her for right now to my own peril. So right now, when we're doing impulse and momentum, there's no new units. We're looking at the same ideas, Newton's laws, forces, mass, velocity. We're looking at the same ideas in a slightly different way that will yield new insights, new ways of considering things. And right now, it's going to be two things interacting with each other. Typically a collision is what we say is happening. So we have an image of people playing rugby. Pre-pandemic, my son is a senior here at Salem State, and maybe you haven't seen me in person. I would have claimed that I was 5'9", but I think in my 50s, I'm shrinking a little bit. Last time I went to get my physical, I'm at the doctor and they're like, oh, 5'7". And I'm like, no, I'm 5'9". And so I stood up as straight as I could and they gave me 5'8". Anyways, my son, we say he's 6'4", only because he would rather not be taller than that, because at certain heights, you're not allowed to go on certain roller coasters at amusement parks, and he likes to go on roller coasters at amusement parks. So he's 6'4" plus. He really looks more like 6'5" when he's wearing shoes. Anyways, a couple of years ago, pre-pandemic, there was a groups and clubs fair, and he decided to try rugby. And if you've never seen or played rugby, it's a little bit scary. But they liked having a tall guy on the team for, I forget the name of the position he played, but they liked having tall guys for certain jobs. Anyways, rugby, rugby player has momentum. Momentum is the product of mass times velocity. And when you have a certain amount of momentum and you run into another human being, you are applying a force to them. So here we're going to introduce a couple of ideas, and you got to let it wash over you for just a little bit. So here is a graph analysis of force versus time. So you can imagine if you push something and you stop pushing, you can look at a graph of the amount of force that you're acting on something for the total time that that force is being applied. Now, for a lot of things like hitting a golf ball, hitting a baseball, kicking a soccer ball, the force starts pretty small. Like, you know, if you're kicking a soccer ball, the force starts when you're, you know, big toe or side of your foot, whatever you do to kick a soccer ball. When the foot is just barely in contact with the ball, I mean, that has to happen, right? You're going from not in contact to kicking. So somewhere along the way, it's barely in contact. So that would be a small amount of force. And then it's in a big amount of contact, fully, you know, at that moment when foot and ball are, you know, fully linked together before the ball starts flying off. And then it gets lower and lower. Instead of actually looking at the force during that period where it starts small, gets big, gets small again, if we just take the average force during that amount of time, we get some interesting insight. So we're going to call that thing, so here's baseball bat and baseball. The F with the solid line over it is average force over a certain amount of time. And because the force is not constant, the force is changing throughout, we have this definition of this thing called impulse. So if I am little else but honest with you, physics is a little bit obnoxious, right? We know this. M stands for mass, right? So force equals F equals MA, lowercase m stands for mass. But if M is the unit, we know that it stands for meters, right? So 5.0 m is a distance, and that's 5.0 meters, as opposed to F equals MA, where M stands for mass. So we've spent a little bit of time talking about energy and work in units of joules, so that's a capital J, but now we're using J in another context, not as the unit, but as the variable in the equation. And here, J stands for impulse. Why not I? Well, we'll use I for other things coming up soon. And we're just using J. That's just the way it is. So J, impulse, the amount of impulse that is imparted to something, is the product of the average force times the time that it's in contact. And for right now, we don't have any new units. So if it's force times time, force is in newtons, time is in seconds, Newton seconds. Newtons, and then that little dot means times, seconds, Newton seconds. So the impulse imparted to the baseball is going to be the average force times the time that the bat and the ball are in contact with each other. Set that thought aside for one moment. That's a thing, impulse. The other major concept in chapter 8 is momentum. You can tell from the title of the slide that we're building up to the impulse momentum theorem, which must mean that impulse and momentum are related to each other somehow, and we will soon find out. But before we get there, we have to define momentum. Linear momentum, and that's as opposed to angular momentum. Angular momentum is another topic that we will cover in this course, and it's different. But right now, linear momentum is the product of mass times velocity. Whenever I think of linear momentum, I think back to when I graduated from college and I loaded everything I owned into my 1967 Volkswagen Bug. That car was as old as I was when I was 22 years old. And I thought, wow, this is really cool. I have a car that's as old as I am. That really wasn't so cool. I don't necessarily recommend doing that. Anyways, I put everything I owned into a Volkswagen Bug, and everything I owned fit inside a Volkswagen Bug. And I drove down the street. And when I got to the end of the street, there's a stop sign, and I stepped on the brakes to stop at the stop sign. And I was surprised because it was taking a little bit longer to stop than I was used to. Why? Because my car had a lot more mass in it. I had stereo and like big stereo equipment and books and whatever. My car was a lot more massive than it usually was. And so it had more momentum. There's some things in physics that aren't what you think they are necessarily. So when we talk about work is the product of force times distance. That's not necessarily what you thought work meant. But for momentum, I think if you have any kind of functional definition in your head about what momentum is, it might be pretty much on target. So I don't know, like if you've ever been like hiking in the woods somewhere, like real kind of camping with a 80-pound pack on your back with your cooking supplies and bedding and clothes and all of that, and you maybe go down a hill and then you're like, whoa, I've got a little more momentum here than I'm used to because I have, a huge amount of weight on my back. So momentum is the product of mass times velocity. The bigger velocity, the bigger the momentum, the larger the mass, the larger the momentum. So, and again, no new unit, so it's just kilograms times meters per second, mass times velocity. So here we are. We have a definition for acceleration. Acceleration equals the change in velocity over time. We also have Newton's second law of motion, which says force equals mass times acceleration. So if we plug in, instead of acceleration, we put in change in velocity over time and then multiply through by mass, we have this thing that says force equals mass times final velocity minus mass times initial velocity divided by time. And then if we multiply time by both sides of the equation, disappears over here, and we get this thing that says force times time equals mv final minus mv initial. This process is essentially what Isaac Newton would have done, saying, okay, we have some definitions, we have some equations, what if we mix them together and see what falls out? And so what fell out is this thing that we're calling impulse that we introduced earlier today. And we said the product of average force times time is this thing we're going to call impulse. And what does impulse do? Impulse changes the momentum of an object. So if I apply a force for a certain amount of time, I will find that the object that I'm applying this force to will undergo a change in momentum, you know, assuming that it's moving, right? So mv final minus mv initial. Sometimes these examples come up at exactly the right time. Sometimes they're a little bit off. So one way of looking at impulse and momentum is if rain comes falling down out of the sky at a velocity of 15 meters per second and hits the roof of a car, it goes splat. It doesn't bounce off. Its final velocity is 0. They're giving us a weird thing here. It's the rate that the rain is falling, mass per unit time, 0.06 kilograms per second. It is something you could determine. If it's raining out, you could put out a bucket, collect the rain for a certain amount of time, get its mass, and then you have the rate that the rain is falling in kilograms per second. And so by taking that information, we can find the average force that is exerted by the rain on the roof of the car. Because what we would do is say F delta T equals mv final minus mv initial. Therefore, force equals mass over time, that's the kilograms per second, times the original velocity of the rain. And so the force is going to be negative 0.06 kilograms per second times negative 15 meters per second. And we get a force from the roof of the car acting on the raindrop of positive 0.9 newtons. That is a very weird specific example, but it's just one way that you can take this information embedded in a couple of equations and manipulate it to find out something new. That's kind of what's going on when we're doing impulse momentum. Likewise, hailstones, if hail falls on your car, the distinction between a hailstone and a raindrop is that the hailstone actually bounces off the roof of your car. If the hail bounces off, then not only do we have an initial velocity, but we have a final velocity. And so since it's final velocity minus initial velocity, final minus initial, that's what we always do for change in velocity, then we would wind up having a larger force because this negative 15 would actually be, you know, positive 10 minus negative 15. Positive minus negative would then be like 25. It would just be a bigger number, which would mean greater force from the roof of your car. Okay. So the work energy theorem that we talked about, that the amount of work you do will either equal the change in gravitational potential energy or change in kinetic energy. And that led us to this idea that there was conservation of energy, that if you're at the top of the water slide, you have a bunch of gravitational potential energy. And as you go down in a frictionless environment, that potential energy turns into kinetic energy, and that the energy is conserved. It's the same quantity in joules of kinetic energy at the bottom as it was gravitational potential energy at the top. For the impulse momentum theorem, we have a similar thing going on where momentum is conserved. However, we do have some rules about that. And momentum is conserved so long as there are no outside forces. So the example that we're showing here is internal forces, two balls bouncing off of each other in a midair collision. Two balls bouncing off of each other. In the x-axis, momentum is conserved because the forces are internal. One ball and the other ball, and they're both acting on each other. For the y-axis, momentum is not conserved. You can see this anytime. I have a ball and I drop it. The momentum of the ball, product of mass times velocity, is increasing as it falls down to the floor. Well, if the ball's moving faster and faster, then momentum is increasing that whole time. That's not conservation of momentum. That's momentum getting bigger. Well, in order for me to fully comprehend conservation of momentum with a ball that's falling, I would have to include the mass of the Earth and the force, and I'd have to include the Earth's gravity somehow in that calculation, which would make it pretty ridiculous to have it be that big and complex. So internal forces are forces that within the system that act on each other. External forces are external to the system. We don't need to go through the calculation. So here's the principle of conservation of linear momentum, that the final momentum of the system, that is a system of, we'll stick with two objects for our purposes, system of two objects where the only forces are each object acting on each other. This does take us back, if I hope you remember, Newton's laws, Newton's first law of motion, second law of motion. Newton's third law of motion is whenever one body exerts a force on a second body, the second body exerts an equal and opposite force back on the first. So here's where that's coming into play. We have two objects that are exerting forces on each other, and something's happening. So the total linear momentum of an isolated system is constant, it's conserved. And an isolated system is one for which the sum of the average external forces acting on the system is zero. We're just taking out anything from the outside. External force would be gravity. External force would also be friction, which is somehow related to gravity, right? But not exactly the same. So it turns out that Isaac Newton did a lot of his thinking about impulse and momentum actually with billiards. There was a billiard table and he would roll the balls around and look at them whack into each other and make some observations about mass, velocity, final velocity, that kind of thing. So if you want to study impulse and momentum, you could play pool. We don't need to belabor this point. After billiard balls collide, friction will play a somewhat significant role, right? So They won't just keep rolling forever until they fall into a pocket. They will roll until they slow down and stop. So just keep that in mind. All right. There are a few types of collisions, for lack of a better word, that we talk about when we're dealing with impulse and momentum. One type of collision is something that we're going to call an explosion, which isn't necessarily as exciting as it might sound. This is an explosion. We have two people that are initially at rest. So the initial momentum of the system is 0. So when they push off of each other and move off in opposite directions, the final momentum of the system is also 0. Momentum is a vector quantity. We can have positive momentum and negative momentum. It's related to the velocity, right? Because velocity can be positive or negative. And so accounting for sign, accounting for a positive momentum and a negative momentum, we have the ability to have the total momentum be 0 afterwards. So momentum final equals momentum initial equals. And so the final momentum is mass of the man, mm, times the velocity of the man, plus mass of the woman times velocity of the woman. And that all equals 0. The initial momentum, neither were moving. The initial momentum was 0. The final momentum adds up to 0. So negative times mass of the man times velocity of the man equals mass of the woman times velocity of the woman. It's supposed to be a W. So what do we have here? The woman has a final speed of positive 2.5, mass of 54. So negative times 88 kilograms times velocity equals 54 kilograms times 2.5. So velocity equals 54 kilograms times 2.5 meters per second divided by negative 88 kilograms. So 54 times 2.5 equals 135 divided by 88 is 1.53. His final velocity is negative 1.53 meters per second. She's moving this way at positive 2.5 meters per second, and he's moving in the opposite direction, 1.53 meters per second. That makes sense because he has a greater mass. So in order for him to be carrying the same amount of momentum in one direction, he would be moving slower than she is in the other direction, given their masses. All right. There's the book working out the solution. So when we're conserving momentum, we want to decide which objects are included in the system. When we look at the system, we need to see which things are internal and which things are external forces. So in order to remove the concern about friction, we have ice skaters on the ice and pretend that ice has 0 friction. We verify that the system is isolated. There's two people interacting with each other, and that's going to be it for what we're thinking about here. And then we set the final momentum of the system equal to the initial momentum and use momentum as a vector quantity, can be positive or negative. So that's the explosion. The other two types of collisions that we'll talk about are elastic collisions, where not only is momentum conserved, because momentum is always conserved, but also kinetic energy is conserved. Kinetic energy is the same before and after the collision. Momentum, remember, has momentum is the product of mass times velocity. Kinetic energy is the product of mass and velocity, but it's 1/2 mv squared. It has the same ingredients, mass and velocity, but it's a different thing. Kinetic energy is always positive. Kinetic energy, when it's conserved, it means the kinetic energy before the collision is the same as the kinetic energy after the collision. There are cases where that's not true, that kinetic energy is lost during a collision. That would be an inelastic collision. The very definition is that kinetic energy is not equal. Kinetic energy is lost during the collision somehow, and that's an inelastic collision. So ideal scenario is an elastic collision where you like take a super ball and drop it on the floor and it bounces back up to the exact same height that you released it from. This doesn't really happen. Energy is lost somewhere. It would bounce lower and lower, unless you throw it down. But if you just release it and let it fall, it won't quite reach the same height. So if you have maybe a normal basketball and you drop it, it bounces up, but not quite to its original height. That's an inelastic collision because it didn't conserve kinetic energy. And then if you have a deflated basketball and you drop it and it just sits on the floor, well, that's completely inelastic. So the two extremes are completely elastic and completely inelastic. And then most of reality is somewhere between the two. An inelastic collision, but maybe not fully so. We don't need to do a ballistic pendulum. We do need, to do a little more elastic and inelastic. I'm going to save that example for Friday. So one other concept, we have impulse, momentum. This other idea, center of mass, just doesn't have a happy place anywhere in the material, so we're tossing it in right here. If I have a ruler and I want to balance the ruler, there's a particular point where I can balance it. That point is the center of mass. So every object has a center of mass, and it's not necessarily the center of the object. So the formula for determining center of mass, if you have a massless, if I said the ruler has no mass and then I put something on it that's not too heavy, but has some mass, like a quarter, then I will find that the center of mass shifts over toward where the quarter is because there's more mass over here, or there's an equal amount of mass on one side of my finger as the other side, even though it's not dead center anymore. So center of mass will matter for certain situations, and we will deal with those when they welcome. Okay. That is enough for today. Let me just look at the chapter 8 homework quick, because I think we're in a good place to break without confusing things. So new share. I have some examples we'll do Friday before I take questions before the quiz. But kinetic energy and momentum. Kinetic energy, 1/2 mv squared. Momentum, the product of mass times velocity. Impulse, momentum. Impulse is force times time. So we have a force. We're going to be looking for time. Momentum is the product of mass times velocity. Number 32, we need a little more. We'll talk about inelastic collisions with an example on Friday before we get to quiz time. But I think that is enough for today. I know that's a lot of stuff coming at you blazing fast, but this is a good breaking point. On Friday, I'll field any questions you have from chapter 7 homework before we have the quiz on chapter 7. So do make sure you take a whack at that. On Friday, we should finish out any questions you would have lingering about chapter 8. So you can look at that for next week. If you haven't had your turn to register for fall classes yet, I hope you've met with your advisor. I hope that you're prepared for that, and I hope it goes smoothly. And that is enough for today. Have a happy Wednesday. I will see you on Friday.
Thank you, Professor. Have a good day.
Have a good day.
Thank you, Professor.
Thank you.
Thanks, you too.
Hi, Professor. I have a question.
Yeah.
Sorry to be a pain in the butt. With regards to my quiz last Friday, I know you've been busy. I don't expect you to have gotten to it. I just wanted to apologize for, I don't know, totally screwing it up.
Well, I haven't looked yet